Now, but what we're doing today is actually we're finishing up chapter P. We're going to be finished with it today. And the last thing we're looking at is inverse function, or finding a function's inverse, which is not anything new that y'all have not done already, because y'all have done this in Algebra 2 and Algebra 1. It's nothing really new. Because when we talk about an inverse, really, we're changing the domain and range. The range is going to become the domain, and the domain is going to become the range. It's flipping it. For instance, the function f of x equals x plus 4 from a set 1, 2, 3, 4 to the set 5, 6, 7, 8 can be written as this, and we can find its inverse. So the inverse is just flipping the x and y values. And when we solve for it, we flip x and y and then solve for y. And if we take the composite function of a function and its inverse, we get back to x. So, for instance, to find the function f of x equals 4x, then verify that they're inverses. So if we go to find its inverse of 4x, we do get this here. Now, the way that we get this is if we start off with, well, it'd be helpful if I can write on the board. F of x is equal to 4x. Our first main step, and it's always been about the same, is to rewrite f of x as y. Then our next step was to switch x and y, mainly just switching their places, and then solve for the value, or solve for y to get y by itself. Divide both sides by 4, telling us y is equal to x over 4, or we could say y is equal to 1/4 x. Either way. And then some of the times we'll rewrite it as f inverse of x equals to 1/4 x, and we have the inverse. Kind of ringing bells again. And if we wanted to check it, all it's saying is that we take f of f inverse of x. Well, we found f inverse of x. It's our 1/4 times x, because we just replaced f inverse with x. F inverse with what it's equal to. Now for f of 1/4 x, we plug this back into our function here, which would be 4 times 1/4 times x. And well, 4 times 1/4 is 1, leaving us with just x. So they are indeed inverses. We can do the same thing going the other direction. F inverse of f of x. But we'll have f inverse, and our f of x is just 4x. And again, we're doing the same thing. This time we're plugging 4x in for our inverse function, which would be 1/4 times 4x. And well, 1/4 times 4 is 1, and again, we do have x. Questions on this here? So really, all this is saying we end up back where we started. Whatever value we started with, we end up back at it. I think this will make a little more sense if I did this here. So domain and range. And what we're saying is the number 4 will say 6. F of x, given a certain function, will take a domain value to a range value. Yes? And all it's saying is that, again, that inverse function undoes it. It takes us back where we started. It takes it from the 6 back to the 4. Or if we talked in a general sense, it's taking x to the y value over here, and then it's taking it right back. So no matter what number we start with, when we apply the inverse and then the function itself, or the function then its inverse, we end up back where we start. That's all it's saying when we end up with x. So does that kind of make sense? Maybe a little more than it did the first time. But that's all inverses are. So then the domain for every x in the domain of G, and for every x in the domain of F. And that's about it. I mean, we can delve more into it, but I feel like for the most part, y'all understand these inverses, understand how to find them. Yes? Now, the graph of them, these inverses are always going to be kind of a mirror of each other. Across the line, y equals x. Yeah, 1 to 1, but there is one, I missed it. There it is. This here is key for if a function has an inverse, or if its inverse is going to be a function, is the horizontal line test. If we can draw a horizontal line and it crosses the graph more than once, it will not have an inverse that is a function. Could it still have an inverse? Yes. But it won't be technically a function. We would have to provide some modifications to it. One of the examples for this here is a quadratic, a U-shaped function, because, well, it's very easy to draw a line and cross the graph twice. It's not going to have an inverse. And the reason that we're saying that is because if it's going to be a function, we can't have one x value for two y values. It just does not work. And we can, because this here we can say is negative 2, 4. Over here we have the point 2, 4. Yes? So this is the graph of the quadratic function. Now the inverse, if it does have an inverse, we flip the x and y. The domain becomes the range and the range becomes the domain. So according to this here, these 2 points are now going to become 4, negative 2 and 4, 2. Yes? I have one x value for 2 y values now. This is why the horizontal line test does not work. Or the horizontal line test works for determining if a function has an inverse. Questions on this here? Now, it is still possible for us to have an inverse with a quadratic. But what we have to do is take one side or the other and say that this function is only for when x is greater than or equal to 0, or less than or equal to 0. Essentially, we cut the half off. That would cause it to repeat or have an image. And when we say this here, we call it 1 to 1. 1 to 1 means that there's a specifically one x value, one domain value for every y. There's no repeats, there's no duplicates. It is 1 to 1. And when we start talking about 1 to 1 or kind of looking more into it than this, and we start talking about injective, surjective, and bijective functions. And there's a way to determine that, but mostly, even in college algebra, we don't talk too much about that or trying to prove that something is a bijective function or bijective. But we have this here. Questions on any of this here so far? Well, finding inverse functions algebraically. As we say in example 1, steps 3, I mean, we've done, use the horizontal line test to determine if it is a function, if it has an inverse. Replace with y, interchange the roles of x and y, solve for y, replace y with f inverse of x, and then we can check it. So, actually, this here is a good one. 5 minus x, 3x plus 2. Now, for the most part, we've found inverses of lines. You've found inverses of some quadratics, but that's about it, because we don't delve too further into this. And I'm racking my brain. Some radicals with square root aren't too bad. This one here is going to be good for us to look at, because the first step replace x with y. Pretty straightforward. Now we need to switch the place of x and y, so we're saying x is equal to 5 minus y over 3y plus 2. So again, not too bad. But now it's getting y by itself. And this part here might seem a little bit tricky. And the main first thing we're going to do, and whenever we come across this, we need to get y out of the bottom of the fraction and then get it by itself, because that's the main goal, is to get y by itself. And to do that, what we can do is I can multiply this side by 3y plus 2. Because again, we would get 3y plus 2 over 3y plus 2, and these would cancel. And what we do to one side, we have to do to the other. And what this ends us up with is we have 5 minus y on the right side. And on the left-hand side, we have the 3y plus 2 times x. We have to distribute this, because there's going to be no way for us to actually separate those apart, the 3y plus 2 apart, without multiplying the x through it. Now, the next main part is to get the y terms on one side and everything else on the other. And this is not as intuitive, and I don't like using the word intuitive, but this process of getting y's on one side and everything else on the other. Because what we can do is I can add y here, add y to both sides, which will tell us that we have 3xy plus y plus 2x equals 5. Then we're going to subtract the 2x, because again, we don't want x on that side, we just want the y's. And what this leaves us with is 3xy plus y equals 5 minus 2x. Questions on this so far? Is there a y term in common on the left-hand side? Well, yes. And what I can do is we can factor that y out, leaving us with 3x plus 1 is equal to 5 minus 2x. And that's why we got the y's on the same side, so I can try to factor it out or simplify it down so I only have a single y term. If we had a y squared term, I would try to rewrite it so it's as a set of parentheses squared. We try using completing the square or these other methods of factoring so we get one set of parentheses to an exponent. Because if we can get it to a set of parentheses with an exponent, we can square root both sides to simplify from there. But at this point here, we can divide both sides by 3x plus 1. It will cause these two here to cancel each other out, telling us that y is equal to 5 minus 2x over 3x plus 1. Or f inverse of x is equal to 5 minus 2x over 3x plus 1. And that'd be it there. Any questions over any of this here? And they're going to show us the exact same thing. And we get this here, and then we can check to see if it is true, and it does work out. And that's what we have for this here. Any questions on any of this here so far? Or, well, that's it. Problems. Seven, 9, and 14. So 7, 9, and 14, you're just verifying that they are inverses of each other. So our f of f inverse of x and f inverse of f of x. Make sure that they both equal x. 15, 17. Verify that f and g are inverse functions algebraically. So again, it's just f of g of x, g of f of x. We're just doing the composite function on those two. Yeah. Determine if 55 through 58 have an inverse. If it does, find it. If it doesn't, just state it doesn't have an inverse. And lastly, 67 and 69. Again, just verifying that it does have an inverse. And that's it. And that is the end of chapter P.